Hey everybody, welcome back. So let's do a couple example problems where we use integration by trigonometric substitution. Okay, so for this first example, it looks like this is in a squared minus u squared form, so I'm going to use a sine substitution. So u is equal to a sine of theta. Okay, if that's u squared, then u is x. And if that's a squared, then a is 2. So it looks like x to the fourth will be 16 sine to the fourth of theta. So I can now replace this and this. And don't forget, I need to replace this. So dx, just by taking the derivative of both sides, is 2 cosine of theta d theta. Okay, so what do we have here? So I've got 4 minus 4 sine squared of theta. So by the way, if I square both sides of this, I can replace this. I think I forgot to do that. That's fine. We've got it. Okay. So that's that. Don't forget about dx. Now dx we said was equal to 2 cosine of theta d theta. So I'm happy about that. And then downstairs we've got this 16 sine to the fourth of theta. Okay, so everything has been substituted. All my x stuff is written in terms of theta stuff informally, right? So next thing I want to do is factor out a 4 here. I could also do a little canceling here as well. So if I factor out a 4, notice I've got a 1 minus sine squared of theta. So here's cosine of theta d theta. And so 2 goes into 16 8 times. And that seems just fine. So now there's a Pythagorean identity I can use because we all know that 1 minus sine squared of theta is cosine squared of theta by this identity. So that's 4 times cosine squared of theta. We've got a cosine of theta right here, d theta. We got over 8 sine to the fourth of theta. So it looks like this right here is going to give me a 2 cosine of theta. I can combine the cosines and I could cancel. I can call this 1/4 and bring it out. Maybe I'll do that. Okay, well, it doesn't look like a substitution would be so helpful right now. Maybe we could split this up. So maybe I could think about this as cosine squared of theta over sine squared of theta times 1 over sine squared of theta d theta. Now I'm thinking that might be helpful because I know that cosine over sine is cotangent and 1 over sine is cosecant. So that means I can rewrite this in the following way. So this is cotangent squared of theta times cosecant squared of theta d theta. So let's write a bunch of information about cotangent and cosecant that might be helpful for solving this. So we know that 1 plus cotangent squared of theta is equal to cosecant squared of theta. That's the last Pythagorean identity. And then let's talk about derivatives. So the derivative of, let's say, cotangent of x is equal to negative cosecant squared. Right, we know that from Calc 1. And what do we also know from Calc 1? Well, the derivative of cosecant is negative cosecant cotangent. And this seems very, very helpful, because if u is equal to cotangent, then its derivative, du, will help with all of this. So that seems to be the route that I want to go. So let's let u equal cotangent of theta. The derivative of cotangent is negative cosecant squared of theta, d theta. I can multiply both sides by negative 1. And that's a very clean substitution. Okay, so I've got negative du for this, right? So that's negative du, and this is exactly u squared. So it looks like the worst is over. This is just the power rule. So I've got minus 1/4. That's going to be u cubed over 3 plus c. I think I'm going to multiply these and also back substitute. So that's going to be minus 1/12. Looks like cotangent cubed of theta plus c. But we want to remember this is a trig sub problem, so we need to go back to variable x. Right? If there's no bounds, I want to use a right triangle to help me get back to variable x. So how do I get my right triangle? I want to go back to my original substitution statement. Remember that? So right triangle, I'm going to go way, way back here. Remember? We had this right off the bat. Isolate the trig function. That will allow you to fill out a right triangle. This is important because it relates thetas to x's and allows me to go back home to variable x. Okay, so sine is equal to opposite over hypotenuse, and you can use the Pythagorean theorem a squared plus b squared equals c squared to find the missing side. This is quite good because I can find the cotangent. Cotangent of theta, that's just the flip of tangent of theta. So that means it's adjacent over opposite. That would be the flip of tangent, aka cotangent. So cotangent cubed. Okay, so again, cotangent is adjacent over opposite. But I could rewrite that like this if I wanted to. And I could write that like this if I wanted to. And there's the antiderivative of our original function. Okay, so I think with that said, we should try one that has bounds as well. Let's try one with bounds. Feel free to rewind, pause, etc. Okay, so let's try this definite integral. So we've got the integral from 0 to 3. We've got x cubed over the square root of x squared plus 9 dx. Okay, so looking here, this looks like it's in the form of a tangent substitution. So I want u equals a tangent of theta, and we want to fill this out. So if this is if this is u squared, right? If this is u squared, then u must be x, and if this is a squared, then a must be 3. Okay, I can find x squared. I can find x cubed. Okay, so I'm able to replace this. I'm able to replace this. I want to replace this, so in order to replace that, just take the derivative of both sides of the x equation. So that's 3 secant squared of theta d theta. So now I can replace all the x stuff. Remember, we need new bounds. These bounds are specific to variable x, right? So change variables, change bounds each and every time. So we need new bounds. So for my lower, let's see how this works. So I want to use my substitution statement. X goes in for x, and I need a theta. So x goes in for x, and I need a theta. So divide each side by 3, and it looks like theta is 0. Now for my upper bound, again, x goes in for x. So x goes in for x, and I need to find the corresponding theta. Well, if I divide both sides by 3, I get the following. And we know that theta must be pi over 4. So there's my upper bound, pi over 4. Okay, so let's rewrite that. I'm going to bring that down a bit. So it looks like we're integrating from 0 to pi over 4. We need x cubed, so x cubed over, down in the radical is x squared plus 9, and then dx is 3 secant squared of theta d theta. Don't forget that. Students often forget to replace this. It's important. Okay, so now everything is replaced. Everything is in terms of theta. It's looking good. We want to factor out a 9 and then look for a Pythagorean identity. Okay, so factoring out a 9, look for a Pythagorean identity. Just combining the 27 and the 3. So I'm factoring a 9 out. That's very nice. Check out that nice Pythagorean identity. We know that tangent squared of theta plus 1. We know that secant squared of theta. So that's 9 secant squared of theta d theta. And so that's good, right? So this will be 3 secant of theta. Let's see if we can reduce this down a little bit. So 3 goes into 81 27 times. So let's cancel these and we'll bring out the 27. Secant will go into secant squared. So that'll remove a copy of secant. And then we've got to do a little bit of work to get this into a nicer form. Okay, so with this, again, so I just want to recall this is a product of tangent and secants. We had some nice ways to think about these. So just quickly, I'm going to write the, if you don't mind, the derivative of tangent and the derivative of secant. Again, I know them. There's just something about seeing them, something about visually seeing them that allows me to make a move when I'm stuck. Okay, well, looks like a couple options to try. Maybe I can try sliding over a secant squared. That's not so helpful or obvious. But maybe I can try sliding over a factor of secant and a factor of tangent. Maybe that'll help me with a u sub. So here's tangent squared. Here's a secant theta, tangent theta, d theta. If that's my move, that should look close to du. So again, I'm thinking about setting myself up for a substitution. And if my du looks like this, then my u needs to look like this. So this needs to be written in terms of secants, and that helps me do that. Okay, so I've got 27 times the integral from 0 to pi over 4. Now this, in terms of secant, is secant squared of theta minus 1. This is secant of theta times the tangent of theta d theta. And now we're set up for a substitution. So u is equal to the secant of theta. Du is that product secant theta tan theta d theta. And don't forget new bounds. We're switching variables. We need new bounds. For my new lower bound, remember use this. So theta, remember these are thetas. Theta goes in for theta, and it kicks out a u. So this is secant of 0. That's the same thing as 1 over cosine, if that's helpful. That's the same thing as 1 over cosine of 0. And so that's 1. So here this is 1. So my new lower bound is 1. Now for my upper bound, now, so u is equal to the secant of pi over 4. And that's equal to the square root of 2. Where did I get that? I used, remember those classic triangles we talked about? This is that classic triangle that's half of a square. So we use these a lot in 7.2. And if I take the secant, which is the flip of cosine, it's hypotenuse over adjacent. This first one came from the unit circle, right? That's from the unit circle. So I've got 27. I've got the integral from, it looks like from 1 to radical 2, u squared minus 1 du. So that seems pretty good, I think. That seems pretty good. So that's 27. I've got u cubed over 3 minus u when I integrate from 1 to radical 2. Radical 2 cubed is radical 8. And this is 1/3, if I plug in 1, minus 1. And there's not much more I could do, but maybe just write this as a single fraction, right? Because these are irrational numbers. They're not gonna nicely combine. I mean, I guess I could call that 2 radical 2 over 3 minus radical 2 over 1 if I wanted to. That would be plus 2/3. And maybe I could combine those if I wanted to. So that's going to be 2/3 minus 1, right? Just looking at the coefficients. They're like terms now. So 2/3 minus 1 is minus 1/3. Oops, that's a 2, isn't it? Well, I guess not so bad. So I guess I could factor out the 3 here. 27/3 is 9, and that's 2 minus radical 2. And that's the value of our integral.